So if you look at this nucleus, beryllium-11. Beryllium-11 is unstable, and we can tell why. If you build it up, it's got 4 protons. 1, 2, 3, 4. Oh, how many neutrons? Beryllium-11, it's got 11 nucleons. It's got 4 protons. How many neutrons? 7. So I build those up in the neutron states. 1, 2, 3, 4, 5, 6, 7 right here. Now we look at this energy state. And you say, from the point of view of the strong nuclear force, neutrons and protons are about the same. From the point of view of the Coulomb force, they're different. But there's something in the nucleus that, like neutrons and protons, tend to be kind of like similar. Wouldn't it be cool if you could take this neutron and turn it into a proton right here? And if you did that, then everything would fit much better. It's just like when I go on trips with the Little Shop of Physics crew, you know, we have like, we rent hotel rooms, and you got like the men's rooms and you got the women's rooms, and sometimes you got like a surplus of one and you have a hole, and you think, wouldn't it be great if I could take one of the members of the team and give them like gender reassignment surgery, and it would just balance everything out so much better. People are always reluctant to do it. But the nucleus, not so much, not so much. I got an extra neutron here, and if it could somehow turn into a proton, it could fit into this energy state right here, and then the overall energy structure of the nucleus would be much lower. And in fact, it does that. Ooh. And the neutron goes and jumps into this proton state. And as it does that, there's an extra proton. There's one fewer neutron. And an electron gets fired off. Because in fact, what happens is this. When beryllium-11 turns into boron-11, which is what it does, the atomic number goes up by 1. The number of protons goes up by 1. The number of neutrons plus protons stays exactly the same. And it does that, and it fires off this free electron right here. An electron comes flying off. And we call this beta decay, and we call this a beta particle. Why don't we call it an electron? Because it's moving at nearly the speed of light. And electrons aren't scary. Marshmallows aren't scary. But if you take a marshmallow and you shoot it at Mach 20, it'll go through you. Okay? And so Mach 20 marshmallow, scary. Electron, moving at nearly the speed of light, scary. It'll damage tissue and it'll damage matter, okay? And so we call it a beta particle. It's kind of a different thing. And so this is a beta decay. Fundamentally what happens, neutron turns into a proton, electron gets fired out. Now there's also a different kind of decay where instead of producing an electron, you produce an anti-electron, a positron. That's the beta plus decay. And you can read about that in the textbook. But there's another type of decay we want to talk about, and that's this. If you have a nucleus which is just too darn big, it's just too big, the Coulomb repulsion wants to make it fly apart. The strong nuclear force tries to keep it together, but the strong nuclear force is short range. If the nucleus is too big, the strong nuclear force loses, and the nucleus does fly apart. It breaks into pieces, and it's almost always true that one of the pieces that it breaks into is an alpha particle. Is an alpha particle, which has 2 protons and 2 neutrons. Oh, what else has 2 protons and 2 neutrons? Helium, okay? And helium is an element that does not occur in the Earth's atmosphere. And the reason it doesn't occur in the Earth's atmosphere is that the atoms are moving too fast, and they just are moving fast in their Earth escape velocity, and they all go away. And so the helium that the Earth originally had is long since gone. But we have helium on Earth because we have helium and helium balloons. So where does the helium come from? It comes from this. It comes from alpha decays of particles in the Earth's crust, and it gets trapped underneath the Earth's surface in certain pockets. Now, why is there radioactive stuff in the Earth's crust? Oh, this is a story. There's several phases to the story. This is just phase 1 of how special these balloons are. Okay, there's more to the story. The minerals that decay to make this alpha particles, this collection of alpha particles that you have in these balloons, were formed 6 billion years ago in one of the most dramatic events the cosmos has ever witnessed. Seriously. That's a story that we'll continue with later. Anyway, alpha particle. It's an alpha particle because it's moving at high speeds and it can damage things. So you have this nucleus turns into that, and it's lost 2 protons and 2 neutrons. And so its atomic number has gone down by 4. I'm sorry, atomic number has gone down by 2. Its atomic mass number has gone down by 4. And so here's a sample alpha decay. Uranium-238 turns into thorium-234. Thorium atomic number 90, uranium's number 92. 92 goes to 90, 238 goes to 234. An alpha particle, helium nucleus, 2 protons, 4 nucleons. Check it out. These numbers balance, 238, 234, and 4. 92, 90, and 2. Because the number of nucleons, in this case, is preserved, okay? So we can balance this kind of equation just like you can balance chemical equations. Sometimes, when a particle, when a nucleus decays by emitting a beta particle, it's left in an unstable state. We say an excited state. And a nucleus is in a higher energy level. And it wants to drop into a lower energy level. And when it does that, it emits a photon. Except the thing is, the difference in the energy levels here is so large that the photon that's emitted has an extremely high energy. And it's not like ultraviolet energy. It's gamma ray energy. It's larger by a factor of hundreds of thousands. That's on the order of mega electron volts. An example, if you have molybdenum-99, it decays into technetium-99 by beta decay. And I have a little asterisk here, and the asterisk tells us that it's an unstable state of technetium. The nucleus is in this excited state. It's like when the neutron turned into a proton, the nucleus was like not in its happy place. It needs to kind of like readjust. And when it does that, it emits a photon, and it's a particularly zesty photon. It's a gamma ray. And so I have excited state of technetium to the ground state of technetium emits this big photon. That's a gamma decay. Does the atomic species change when that happens? No. Nor does the isotope. The number of protons and neutrons stays the same. And you're saying to yourself, Brian, I'd like a chance to try some of them balance an atomic number during radioactive decay problems. Oh, yes. Here's your chance. Right here, first one, strontium-90 decays by beta minus decay. Okay, strontium-90, beta minus decay, gives off an electron. When it does that, what does it turn into? What is the daughter nucleus? I want you to talk to your neighbors about this. I'm going to call for a vote in 30 seconds. What are you thinking? Let's talk this one through. What do you say? Let's talk this one through. Okay, strontium-90. Here's the first piece I do. I write this down. I have to do it even now. I'm going to write down the isotope. It's strontium-90. That's the atomic mass number. But I'm going to write the atomic number down, too. And I've got a little snippet of the periodic table right there. And I can see it's atomic number 38. It decays by emitting an electron. Now, when it does that, it turns into something which has more protons, right? Because a neutron turns into a proton. So it goes from 38 to 39. That has one more neutron. I'm sorry, one more proton. Now, if a neutron turns into a proton, what happens to the total number of protons and neutrons? Same. The sum is the same. And so it's this, 90, 39. And then I look that up in the periodic table, and it looks like, oh, it's yttrium. Sorry, wrong periodic table. It's number 39, yttrium, and so it's a Y right here. Another thing you can do is this. I'm going to put a 0 up here, and I'll put a -1 down here. The number of protons, you can also think about this as the number of positive charges. Or you can think about this number as being the charge. 38 goes to 39. If the positive charge increased, it has to get rid of a negative charge because 39 plus -1 is equal to 38. Number of protons and neutrons, 90, is equal to 90 plus 0. So this balances, and everything works out. And so we can do the equations that way. How about the next one? If we look at the next problem. Radon-222 gives off an alpha particle and turns into what? Talk to your neighbors about this. I'll call for a vote in 30 seconds. All right, let's take a vote. It's B. It's B. And we can figure out why. It's lost an alpha particle. I'm just going to write that as a helium nucleus, which has got a 4 up here and a 2 down here. And I'm going to fill in the periodic table. Well, let's see. Radon 222. Its atomic number 86. So I'm going to put an 86 here. It lost 4 particles up top, which turns into 218. It lost 2 particles down below, which turns into 84. And so it's turned into element number 84, and the specific isotope is 218. 84, polonium 218. So it turns into PO 218. This is happening in the room. This is happening in the room. Turns out we have a fair amount of radon gas in the air in Colorado. Why? Because we have a fair amount of uranium in our soil. And uranium ultimately decays, and there's a decay chain, and it turns into radon. So we have radon gas in the air in the room. When it decays into polonium 218. Now here's the thing. Radon's a noble gas. An atom of radon is very happy to float around the room. But polonium's a metal. An atom of polonium does not want to float around the room. And so what it does is it'll stick to something. It'll glom onto a surface. And what it'll do is it'll glom onto a dust particle. If you take a balloon, blow it up, rub it on your hair, it becomes statically charged. And if it becomes statically charged, it'll attract dust particles. And if I take this balloon, blow it up, and rub it on my hair, not only will it give me a good look, oh yeah, not only will it do that, it'll also become radioactive because it's going to attract dust particles which have like polonium and all these kind of like radioactive daughter products on it. Seriously, this balloon will be measurably radioactive by the time class is over. Seriously, it's quite remarkable. Now, you don't have to collect it that way. Oh, by the way, too, the balloons that you all got, they rubbed together when I was bringing them over. Static charge, radioactive. Oh, yeah. That's another element of the specialness of these balloons. Here's the thing, though. You're already subjected to this radioactivity. This is part of nature, and it's a piece that we're going to talk about in the lab this week. But let's look at this. Determining the decay mode. Suppose you're given this nucleus, and it turns into this nucleus, and I want to know what kind of decay was it. Emitting an electron, emitting a positron, alpha particle, gamma ray. Which one is it going to be? So go ahead and take a look at this decay. I want to predict the decay mode. Talk to your neighbors about this. I'll call for a vote in 30 seconds. All right, let's take a vote. It's beta minus decay. Here's how we can figure it out. Cesium-137 to barium-137. Does the number of protons plus neutrons change? No. Which means we can immediately rule out alpha decay. That's not possible. If it's a gamma decay, does the atomic species change? So we can rule out gamma decay. That's not happening. It's either beta minus or beta plus. It's one of those two. And let's look at our periodic table. Cesium is atomic number 55. Barium is atomic number 56. So I've increased the number of protons. So what that tells me is a neutron turned into a proton, which is exactly what happens in a beta minus decay. Okay? It's the beta minus decay. It's answer B here. That's what we're looking for.